before. We're Vistar Media. We do a lot of geospatial marketing technology. I like to think of it as like kind of an adult engineering team that takes time to research, code review, testing, things like that. Company is 5-6 years old. Split between here and New York as an engineering only office. I suppose if you have any questions, just grab me or someone else. We've got 2 presentations tonight. Bogunovich is going to talk about OR tools and optimization research.
Operational research. Operations research.
So, a tool from the library from Google use. And Derek Benson is going to talk about geospatial indices, which comes up a lot. So, thanks for coming out. Enjoy the beer. All right.
Woo! So, hello. I'm Bogunovich here. And today we're talking about OR tools and combinatorial optimization problems that we deal with in Vistar. So it's actually a little more focused on the problems that we deal with in Vistar, but there's also some discussion of like using OR tools, which is something that we can also use. So next slide. So what are the OR tools, you may be asking? Well, next slide. Obviously, it is Google's open source library for creating Rushmore memes. The classic Wes Anderson film. We can never forget this scene where Jason Schwartzman asks Luke Wilson's character about the nurse uniform. Anyway, so actually, that's not what they are. According to Google's definition or description, the OR tools are a fast, portable software suite for solving combinatorial optimization problems. And as you said, Mark mentioned, the OR really stands for operations research, which is just like a businessy name for these types of problems that's been around for like a long time. So what is combinatorial optimization, you may be asking? Well, that's obviously the problem of finding the proper variety and quantity of each flavor combos for your next party, which also not really true, but you could very easily create a combinatorial optimization problem from like that particular thing. You would say like there's different flavors and only certain people eat certain flavors and they cost different things. So you want to minimize the cost of buying your combos while satisfying all of your guests. That would be like a legit combinatorial optimization problem. Anyway, going back to Google's description, combinatorial optimization is the approach to finding the best solution out of a very large set of possible solutions. So when they say very large, that typically means like brute force iteration is just not going to cut it. It's just like there's too many possible solutions. So what you need to do there is just figure out a way to limit the search space, or like find a way to guide your search in order to get a reasonable performance. So what are some examples of these problems? Well, really, I mean, most classic CS algorithms can be kind of phrased as combinatorial optimization problems, like, especially graph algorithms like traveling salesman, minimum spanning tree, Dijkstra, and then a lot of like these NP complete or NP hard problems, also combinatorial optimization problems. Then you have this other category of like linear optimization, which my combinatorial optimization problem falls under. And then there's something called constraint optimization, which is things like these N queens problem, which people might have heard. It's like been sort of popular in the news lately, which is like the idea of you have a checkerboard or a chessboard with like N columns and rows, and you want to figure out how to place the N queens on there so that like no queen could attack any other queen. And also there's like these crypto arithmetic problems, which is like, this is the classic send more money, which says like, you want to assign a digit to each of these characters so that like that's actually true. Anyway, just a little background on this library itself. So it's written in C++, but it uses a Python program called Swig that translates the code into a bunch of different, basically, I don't know, whatever language you want, Python, Java, and C#. So it's supported on Linux, OS X, and Windows. We've mainly used it on Java on Linux, and there's a lot of documentation in terms of like installing and running programs. Also, tons and tons and tons of examples that are in the download, the archive, or whatever you get from Google. Just like some real basic whatever about running a Java program with OR tools. So obviously, just include the jar in your class path as you would with any other third-party library. And then you just have to specify the location of those C shared libraries or shared objects with this your Java library path. And then finally, this is something that people don't typically see in Java programs, but this load library that just tells the JVM to load that shared object. So just a high-level overview of like what is in this suite of software. And this is again coming directly from like their documentation. So there's a constraint programming solver. There is a simple and unified interface to linear programming and mixed integer programming, which basically means, if you don't have any background, but linear optimization is like a very popular, very old field of research, and there's like tons and tons and tons of libraries out there for solving these problems. So what they're saying there is that Google has their own linear optimization library that's included in OR tools, but it also is capable of like plugging into a lot of very popular third-party ones as well. So that's what I mean by like unified interface. Graph algorithms, so like some of the most popular graph algorithms are in there. And then there's some stuff for like doing some of these like NP complete problems, like traveling salesman and bin packing and knapsack. So for our talk, we're going to focus on the things that we've actually like experimented with at Vistar, which are linear programming and MaxFlow. So what is linear programming? Well, linear programming is a form of mathematical optimization that has absolutely nothing to do with computers. It's just the word programming there is just like a misnomer. I mean, it does because you can write a program to solve them, but you can also just whatever. So the basic idea is that you have a set of linear constraints over some set of variables. What that means is like each constraint is a linear function of your variables. And then you also have a linear objective function over the same set of variables. So you have like a whole bunch of linear functions or linear inequalities, really. And the goal is to optimize, which means either maximize or minimize that objective function while also satisfying the linear constraints. So here's like a canonical form for a linear program, which basically says maximize this objective function subject to these constraints, where A and B are your constraints, and X is the variable. So here's an example stolen directly from the documentation. So your objective function here is maximize 3x plus y subject to these three constraints. So you have x plus 2y less than or equal to 14, 3x minus y greater than or equal to 0, and x minus y less than or equal to 2. So if you were to like take these three inequalities and graph them, what you'd wind up with is something like this. So this triangle. So like these are like the three lines, and the intersection of the three is what is called a feasible polytope. So polytope just basically is like a fancy word for a geometric shape with flat sides. So in this case, it's just a triangle. So I guess any point in here, any point that's within the feasible polytope will be considered like a feasible solution to the linear program. And the goal is to find the point within that feasible polytope that actually maximizes your objective function. So, walking through the example with OR tools, the first step here is, and this is like the Java example, the first step here is creating the solver. So the only interesting thing to pay attention to here is the fact that we're using the GLOP or GLOP, I don't know how you want to say it, but GLOP, the linear programming solver, which is Google's linear optimizer. And as I mentioned, there's a whole list of other libraries that they support. So this is just like the default one. Then the next step would be declaring your variables. So here your variables are x and y. So pretty straightforward what's going on here. You're just using the API to make a variable called x and a variable called y. And if you notice when you're invoking that, you're basically saying what the bounds are on those variables. You're saying that the lower bound on x is 0, and the upper bound on x is infinity. And the same thing for y. And then the next step would be defining your constraints. So you have 3 constraint functions. They're defined in terms of your variables, of course. So it's a little bit, maybe a little awkward to see the syntax here at this first line. But what you're saying there is that when you say negative infinity 14 there, we're saying is that this first constraint has no lower bound, which, I mean, you can see from right there. The lower bound is negative infinity. It just has an upper bound at 14. And then the rest of it is just pretty clear. You're just setting your coefficients. So you have like 1x plus 2y. And then the second, well, go back one slide. So the only other interesting, I mean, not really that interesting, but the second one, it's the inequality switched. So you see there's a lower bound and no upper bound. Other than that, it's pretty much the same thing. And then the next step, defining your objective function. So this is pretty straightforward. So you're just setting the coefficients on your variables. So 3x plus 4y is your objective function, and you just have to tell it that I would like to maximize that function. So then finally, just invoking the solver and printing the results. So I mean, right here you can see the line where you're invoking the solver, and then it's just printing the results. So these are what you get from when we run that program. The number of variables is 2, the number of constraints is 3, and the optimal solution lies at x equals 6, y equals 4, which will yield an objective function value of 34. So if you go back to this like geometric interpretation, this is just like a few words on like how this thing kind of works under the hood. So if you go back to this geometric interpretation, you can actually see that like the objective function is just another line in terms of those variables, or a plane if there's more variables. So what you could do, so you see basically where this line intersects the isotope, or I'm sorry, the polytope at 6, 4. That's where your optimal solution is. And you can kind of envision, if you were like thinking about this geometrically, that you could just slide this line. I mean, the slope of the line is fixed, right? It's like fixed by the 3 and the 4. But you could just slide it down, and you'd see like, okay, at some point I'm going to leave the feasible polytope. And turns out that like that point where you leave the feasible polytope is always going to be one of these extreme points. So even if you go to like a 20-dimensional, if you 20 variables or whatever, you can't really visualize that geometrically. But like, the fact remains the same. It's like you can do the same thing, just slide it through, and you're gonna the optimal value, whether it's a max or a min, it's always going to be at one of those extreme points. So we jumped too fast. So with that observation, what happened was that when you make that observation, you no longer have to like search through a whole infinite space of this feasible polytope. Really, all you have to do is just explore each of those extreme points. And the person who discovered that was, of course, horror metal legend Glenn Danzig. And actually, that's not true, but it was this guy right here, George Danzig. And there's a T. So he was worked for the Army in the 1940s, and he made that observation and developed what is called the simplex algorithm. So the way that works is basically it's just a smart way to traverse those extreme points until you find the solution that is the optimal one. And there's a lot of linear algebra in there underneath and whatever, which is not really that worth going into. So how do we use linear programming in Vistar? Well, you need a couple definitions here. So First of all, impressions are a number that loosely quantifies the number of people that will see a particular ad. CPM is just cost per, it's actually cost per 1,000 impressions, but for our purposes, you can just say it's cost per impression. Budget would be the total amount, be it in either cost or impressions, that an advertiser would like to spend. Insertion order is an object that has both a budget and many campaigns. And then what is a campaign? Well, a campaign is just like a part of an insertion order. So it has some targeting associated with it, a capacity, and a CPM. And what needs to be done is you need to assign it a budget. So the problem that we have here is, given an insertion order's budget and the campaigns, capacities, and CPMs, what we'd like to do is like pick the optimal budget for each campaign. So more formally, you say that order has a budget of B, whether it's in impressions or cost, and the order has N campaigns. So campaign I has a capacity of AI and a CPM. So there's AI total impressions and the CPM is CI. And then you have these variables XI, so like X1, X2, whatever. And those are the variables that represent the impression budget of the campaign I, and that is what we want to select the optimal value of. This is just like the same thing I just said there. I just left it there so that people could like not get lost with the next slide. They're like looking at this. So your constraints are that you have your impression budgets for each campaign has to be greater than or equal to 0. You can't have negative impressions. And it has to be less than or equal to the total capacity of the campaign for each campaign. And also you have that if you add up all of the campaign impressions, they should equal the budget of the insertion order. So then here you have like an objective to maybe minimize total cost. So you're just like multiplying the CPM by each impression allocation, and that's your objective function. Or if the budget is in terms of cost and not in terms of impressions, then it's almost the same thing, except now you have that the costs should all add up to the budget of the insertion order, and in this case, you might want to maximize total impressions. Sadly, this isn't like the most useful formulation, because if you fed that into a linear solver, what that's going to do is basically just pick the cheapest campaigns first, and you're going to wind up with most of the campaigns will have no allocation, which isn't really what most advertisers want to do. They don't really want to just buy the cheapest ads that they can get. So what they really want is something more like a evenly distributed order, which means that to achieve that, you want to do something like minimize variance across the allocations. And sadly, variance is not a linear function, so we can't really use OR tools to do that. And we wind up not using it, so we wind up using NumPy for this problem, which is internally uses something called sequential least squares. But that's not to say that there's definitely a lot more that we could explore and should explore with linear programming or even using NumPy. One of the big things that linear programming really excels at is expressing relationships between the variables, which we haven't really explored at all. So you can say these two campaigns should not have more than half the budget or something. That kind of stuff like that. It's is really where it excels. But the story is here is that we went down the OR tools path with this, but we wound up having to use something slightly more complicated linear solver. So that brings me to the second topic, which is max flow. So max flow is a graph algorithm, and it is designed to model transportation of goods across some kind of network, the network being the graph. So that network could represent any sort of thing that you can think of that can be represented with the network. For example, railroads, internet, whatever. So this is I think this is a railroad map of Germany from the early 20th century. each edge in the network has a capacity, and then along with that network and capacity, you also have a source vertex and a sink vertex. So the goal of the problem is to push as much stuff from the source vertex to the sink vertex while respecting all of the capacity constraints. So more formally, you have definition like G is your graph that consists of a vertex set, an edge set, a source vertex, and a sink vertex. T is the sink. That's just like, I know, can't use S twice. And then C is your capacity function, so it just maps each edge to a positive value. And then a flow is just a function that maps your vertex pairs of vertices to a number, such that the flow of any pair of vertices has to be greater than or equal to 0 and less than or equal to the capacity of that edge. So you can't push more flow than what the capacity of the edge is. And secondly, you have this thing called, which is like flow conservation, which basically says that the amount of flow going out of a vertex has to equal flow going into the vertex, except for the source and the sink, because they're the source and the sink. So then the value of the flow is just a number, which we call, or which is defined as the sum of all of the flow out of the source minus all of the flow into the source. So it's really just the positive flow out of the source. And then the maximum flow is just the biggest possible flow that you can get for that particular network. So here's another example. This one is just, it's in Python. They didn't have Java example on the documentation. So here you have your source is this vertex 0, and your sink is this vertex 4. And the first step here is just defining your edges with their capacities. So pretty straightforward to read through here. It's like there's parallel arrays. So like vertex 0 to 1 has a capacity of 20. So 0 to 1 has a capacity of 20. Nothing too exciting there. So next slide.
Locked up.
Locked up. Okay. Let's go back to present.
Where's present?
Over on the right.
Yeah.
Okay. So the first step here is just creating the solver and then telling the solver what the structure of your network looks like. So I mean this is pretty straightforward code to follow here. You're just getting a new solver and then just defining a start index for end index and capacity. And then finally, you're just invoking the solver and printing results. So one interesting thing to pay attention to here is that when you invoke it, you are specifying what the source and the sink are at that time. So what does that give you? Well, it tells you that the maximum flow is 60, and it also defines what that flow looks like in order to achieve, like what the assignments are to each edge in order to achieve that flow. So you can see, okay, like from 0 to 1, my flow is 20, and then from 1 to 4, my flow is also 20. So you can see, like, here the flow is less than what the capacity is. And then, so next slide. Another thing that it tells you that's interesting is this information about the min cut. So there's like an important theorem in network flow called the max flow min cut theorem that says that so a cut would basically be like a set of edges that you could remove from the graph that would like separate the source from the sink. And the min cut would be the set of edges whose summed capacity is the smallest possible that would remove the source from the sink. So the theorem states that like if you sum up all the capacities of that min cut, that's going to equal your max flow. And I mean, it's pretty intuitive if you think about it. It's like that's the bottleneck of the network. So it also tells you what those bottlenecks are. So and it tells you it twice. So the source min cut, it basically says if you remove all of the edges going out of 0, then that is your min cut. So you can see like 20 plus 30 plus 10 is equal to 60, which is the max flow. And it also tells you the sink side min cut, which is all the edges going into 1 and into 4. So you remove this one, that one, and this one, and you got to know you get 20 plus 20 plus 20 is 60. So some interesting stuff to if you want to do some further analysis of your network, find the bottlenecks. So how do we use max flow at Vistar? Well, we have people that are media owners who own screens, and then we have buyers who are advertisers who are trying to place ads on those screens. So we'll get these requests from the media owner or from the buyers to the media owner, say like, I want to, this is the kind of inventory I want to buy. This is my budget. What can you give me? And so when the media owner receives that request, he needs to go back and run availability and see if it's doable. So when he does that, internally we have these things called proposals, which basically are just a model of a request from a buyer to a media owner. The proposals are either in an open state or a booked state. Booked proposals are guaranteed, which means that you cannot have two booked proposals that contradict each other. So the guy ran his check, and he found that there were 12 million impressions available. So he goes back and tells him, hey, I can fulfill your request, and now he can book his proposal. So now somebody else comes along, and she's asking for the same thing. So the guy, at this point, he can say, well, there was only 12 million impressions available, and I already booked 10 of those. I can't give you the whole 10. I can give you 2 million. Okay. So how does that workflow work? How does that go in our system? Well, the media owner would create a new proposal and then attempt to book it. And then Vistar will internally create a flow network that consists of all of the media owners' booked proposals and the new one, the open one. And the edge capacities in that network are defined by the impression requirements of each of the proposals and also the media owner's impression capacity. So then we'll run the max flow algorithm on it, and so in that resulting flow, if all of the proposal impression requirements are met, then it's okay to book the proposal. If any of them are not met, then there's a problem and we cannot book it. So, more formally, we have the media owner's impressions are distributed across these screens, individual screens that we call units. So you have like n units here. And then we have something called an impression capacity function that takes a unit and a date-time range, and it gives you a number of impressions that are available on that unit during that time range. We require the date-time ranges to be an hour of the day, so that's like our smallest level of granularity. So for example, like 9 a.m. to 10 a.m. on today, September 13th. So we would call a date-time range, T on a unit U, a slot. So for example, this function might tell you that during that hour on today, unit 1 has a capacity of 4,000 impressions. So when constructing this graph, we make a vertex for every booked proposal, the open proposal, every relevant slot. So when I say relevant, that just means like it has to be relevant to some proposal in our set of proposals. And then we make an artificial source and an artificial sink. Then we add an edge from the source to every proposal vertex, and the capacity of that edge is equal to the proposal's impression requirement. Then we add an edge from each proposal vertex to all of the slots that the proposal is targeted towards, and again, the capacity is equal to the proposal's impression requirement. And then finally, And then finally, we also add an edge from every slot to the sink T, and the capacity of those is equal to the capacity of the slot. So it's like it has nothing to do with the proposal's impression requirement. And here's an example. So you got your source and your sink, and then you have this tier of proposals, and you have this tier of slots. And you can see what the definitions are. So like these are proposal requirements, and then these are like capacities. So you can run the max flow on there, and you can see, okay, like this one is okay, and you can actually see that just by looking at these edges going out of the source. So if you see that, like, this guy asked for 20 impressions, he got all 20. This guy asked for 30 impressions, he got all 30. And this guy asked for 30 impressions, got all, or 10 impressions, got all 10. So, like, you don't really need to look anywhere else to just be able to figure out, like, it's okay to book this proposal. So at Vistar, we use this sort of approach to check availability for media owners that have over 3,000 units, and currently they have over 600 booked proposals that we're looking at. And the resulting problem that we get from that has over 20 million vertices and over 150 million edges. So in order to construct and solve that problem, it takes about 35 seconds. And about 30 of those seconds is just running database queries and like timed computations to build those slots. It's really like the OR tool solver only takes about 5 seconds on a problem of that size. So internally, OR tools uses something called a push relabel algorithm to solve the problem. So there's like a ton of different implementations to solve max flow. Push relabel is like probably the fastest or one of the fastest. And there's like different varieties of push relabel algorithms. But there's other ones that are like much simpler if you just want to understand the problem. But they use a really fast one. So going back to our example, remember, like, we found that there's only 12 million impressions available. And he didn't just tell her, like, no, I can't do it, but he also said, I can't do it, but I can give you 2 million. So, so next slide. So how did he know that there were 2 million impressions available? Well, you don't, if you think about it, like, what I just described there wouldn't really tell you that for sure. What we'd like to do is not just give a yes or no answer, but also be able to say, if the answer is no, it's also like, what could you do? Like, which is, whatever. So we actually came up with a way to do that, which we call maximum flow query. So here's like the general steps on how to solve the problem. Number one, we construct the problem the same way I just described it before, but we omit the edge from the source to the open proposal. Then we find the max flow on that problem. That problem should always be feasible. You should always be able to satisfy those proposals because they're already booked. There's no edge from the source to the open proposal, so there's no way you can push flow to it. If that isn't feasible, then there's like something went wrong with our database and not good. So you take that first flow and then you subtract the flow values from the edge capacities and you add these reverse edges with the capacity equal to the flow over the original edge. So if there was an edge from U to V with a flow of 20, then you would make, in your new graph, or in the updated graph, you would make an edge from V to U with a capacity of 20. So then you remove the edges from the source to each of the book proposals, and you add the edge from the source to the open proposal. And finally, you find the max flow on that problem. So then the value of the flow from the source to the open proposal in this problem is going to equal either the amount of impressions that the guy requested, if the problem is feasible, if you can book it, or it will be the maximum amount of feasible impressions that you could book while respecting all of the booked proposals requirements. And then you can take these two flows, we solve two flows here. You can take these two flows and sort of add them together, and the result will be a maximum flow that respects the booked proposals impression requirements. So here's an example. I just changed the numbers from the previous one a little bit to make it so that it's not feasible. So the first step, next slide, is removing that edge from the source to the open proposal. So then the next slide is we solve the max flow. Notice like there's nothing going through that open proposal. So you have your initial flow right there. And then it's kind of hard to go and see that transition because a lot of things happen between those two slides. But you took the first flow and you subtracted, so the flow over this one was 15 from B1 to S2. So we took that 15, we subtracted it from the capacity so that 20 remains. It was 35 and now it's 20. And we also added an edge from S2 to B1 with a capacity of 15. And then we removed these booked proposal edges and we added the edge back to the open proposal. So then we solved the max flow on that one, and what you see here is that, okay, it's able to, it's some interesting things going on here. It's able to push 15 impressions through slot 1, so from the open proposal to slot 1 to the same, just like how it was doing, with the other flows. But the thing that's kind of interesting here is that it's able to take 10 impressions, push it from the open proposal to slot 2, and then redirect those impressions back to the booked proposal 1, and then redirect those 10 impressions to slot 5 into the same. So what the match flow algorithm does sort of automatically is it redirects the impressions when it can, which is like kind of a really nice property of this thing. So then finally, we would just like take those two flows and add them together. And what you see here is like, okay, these flows are, these requirements are respected, but sadly this guy could not get his 30 impressions, he could only get 25. So this formulation, it only, or this algorithm that I just described there, it only really works because of the structure of our graph. You can't like use this with a general flow network. You can easily come up with an example that where what I just described would not work. I read that there were some like general solutions for that, but they have like a very, very, very complicated networks where you have to like make all these crazy edges all over the place that I'm like, anyway, this is a lot easier. Some final thoughts. So one kind of important thing that I would say about these combinatorial optimization problems, it's very, like, sometimes it's really difficult to formulate your problem and choose the way that you want to go about solving it. So, for example, max flow, you could formulate that problem as an integer programming or linear programming problem, like the example that I did before. But if you did that and you tried to solve it, you would get like much worse performance than if you would go about like solving using the push relabel or even like the Edmonds-Clark algorithm to solve it. So like the way you formulate your problems is very important. Sometimes, well, I guess that's enough to say about that. Another thing to mention is that the reference docs are very good, but they're all C++ reference docs. So if you want to like, you're using Java or Python, you have to do like some sort of mental conversion between like the function names or whatever, which is not hard to do, but it's just like, watch out for that. And then building the project requires just a little bit more effort than what you're typically used to when using a third-party library, just mainly because there's that shared object. It is very actively maintained. It seems like they have a release every month for the past few months. So each release has like new features, improvements on the performance of algorithms. This is like really, it's like a huge library that covers a huge breadth of problems. I didn't even talk about like the constraint programming, which is like a pretty interesting kind of field. That you can just get like lost in these examples for days, just trying different things. And finally, I'd say like it has a very flexible interface, particularly with like the linear programming stuff. Like it's hiding a lot of ugliness that goes on in constructing these problems for the user, and the performance is very good, as you noted by the fact that we were able to solve a 150 million edge network in like under 5 seconds. Actually, it solved it twice because it's doing that like 2-step flow. So, and finally, I leave you with a photo of Glenn Danzig buying Kaler. If anybody has any questions or if you want to talk afterwards, I'll have to do that. Otherwise, I'm just going to sit down.
Cool. You want to take 5 and then we'll do some of these.